Thank you everyone for joining in. I'm going to be telling you today about how to handle dependent censorship in survival analysis. And so this is joint work with Russ Greiner, who's over at the University of Alberta, and Amy, as well as our two students, Michael and Ali, who worked together on this over the last year. So I won't belabor too much on this point, but like Foomani mentioned, one of my research goals is to think about how machine learning can assist in the creation of a learning healthcare system. So where we go from scientific discoveries, which eventually become biomarkers in an electronic medical record, which then advance the ability to predict outcomes or find digital twins, and that in turn improves our understanding of disease biology itself. So what I do research on can be broadly classified into two groups of work. So the first one is this pull thread where we look at clinical data, work with clinicians, and ask what are the interesting learning problems that have been understudied in the machine learning community, and what are the advances in machine learning that we need to create in order to actually tackle those problems. And the other one is more of a push thread where we take some of the new advances in machine learning and deploy them on interesting clinical problems. And so this talk sort of falls into the former category. And if at any point you doze off or fall asleep, you should take away this one slide from the entire talk. So really, what I want to do today is to tell you about dependent censorship. I want to tell you what it is and why you should care about it. I want to tell you that a lot of methods for survival analysis that you may have heard of or use assume that data is censored conditionally at random. And so I'll explain what that means. Dependent censorship can occur in real data, and I'll provide some examples of it. And finally, what this paper and method is really about is how to handle dependent censorship in nonlinear risk functions. And along the way, as we sort of explored this question over the last year, we sort of came upon several different insights about evaluation in survival analysis, as well as the connections that it has to causal inference. So I'll touch a bit upon that as we go along. So to start off, and this may not require too much elaboration, really it's going to be about prediction in biomedicine. And so a lot of tasks that you may have heard of over the last 3 weeks would require some form of a predictive model. And we might be interested in predicting the onset of an event in the future. And this shows up in genetics. This shows up if you're making risk stratification in clinical data. And we might want to predict things like time to mortality, given genetic sequence data, or predict the relapse of a cancer after treatment, given some clinical biomarkers for a patient. The problem, however, is that in real data, we run into the problem of missingness, and particularly missingness in outcomes, which is to say we don't always observe the outcomes that we care about. And so there's many, many reasons why that may be the case. So in the 4 patients that I showed you over there, as an example, we might observe the outcomes for patients 1 and 3, but patient 2 might have withdrawn consent to be in the study after a certain point in time. Patient 4 might have just moved to an entirely new city and can no longer be part of the study that one is collecting data for. And so the question arises, what should we do with such data? And so here's a pictorial depiction of, say, the events corresponding to 4 patients. And the first and the third are events that we actually observe at the blue dots. And for the second and the third patient, we don't actually observe the event. We only observe patient data up until a certain point in time. And so this kind of data is called right-censored data. And that's going to be the object of a lot of what I'm going to talk to you about today. We have 2 options if we're collecting a large biomedical data set and we run into right-censored data. Option 1, which is highlighted in red because it's not a great option, is to throw away all of the censored data. The problem is that in most studies, if you're working with a few thousand patients and 500 of them are censored, that's losing a lot of information. And so you want to keep them. And keeping that data while still building predictive models of the outcome of interest is largely what the field of survival analysis is really about. How do we incorporate right-censored data into time-to-event predictions? So our goal is to build a predictive model of an event. We're working with data that is right-censored, and so data that looks like the pictorial diagram here. And so as a starting point, I wanted to highlight some of the differences between regression and survival analysis because it's instructive as we build along the mathematical foundations of what we might need to reason about dependent censorship. So in regression, we start off with some data sets, xi, yi, where xi is the vector of coefficients and yi are the outcomes that you care about predicting. So we'll focus on a real valued outcome such as a time to mortality as an event. And the learning goal in regression is really to maximize the conditional likelihood of the outcome given the observed data. So we want to maximize probability of Y given X for each patient. And our machine learning model is really this function F that we learn via empirical risk minimization. In survival analysis, on the other hand, the data that we get takes the form of this triple, where for each patient, we have Xi, a vector of coefficients, Yi, an outcome, and a delta. And delta is really an indicator function, where if delta is 1, it means that that patient actually had an event at the observed time Yi for that patient. If delta is 0, it means that that patient was censored, and that Yi simply represents the last observed time for that patient. So when we moved to survival analysis, and just to belabor the point a bit, to think back to the example I gave with the 4 patients, for patients 1 and 3, you would have delta equals 1 because you actually observed that time point. And for patients 2 and 4 who were censored, you would have delta equals 0. And the Yi's for each of those patients would represent the last observed time points for each of them individually. So we're in a scenario where we have to learn with this 3 sets of information. And the learning goal changes slightly. For the set of patients that we do observe, we still want to maximize the likelihood of observing the event under the model, which is this first function F that you see here. But for the second group, for those who are censored, we work with what is known as the survival function. And the survival function is simply the probability that the event occurred after the last observed time point. So survival analysis really is about learning with these 3 sets of information rather than the 2 that you traditionally get. And just to contrast the loss functions or the learning algorithms one might use for survival analysis, at the top is what you would recognize as the likelihood function for regression. So you have the product of the conditional density associated with each of the data points. And at the bottom is a often used loss function for survival analysis, where you have the event loss that is raised to the exponent of this delta indicator variable. So it's only active when the patient observes an event. And the censoring loss, which is the survival function of the distribution that is only relevant when the patient is censored. So if you were to translate the second equation into English, what it's really saying is if you have a patient for whom you observe an event, maximize the likelihood of the distribution. If you have a patient for whom you observe for whom the data is censored, maximize the survival distribution for that patient under some parametric model that you're going to build. So that's the setup really for the problem. And maximum likelihood here, I won't delve into the math of it, but you can write down closed form solutions for the likelihood functions, both 1 and 2, if you make parametric assumptions about the conditional distributions. Yeah?
At this point, you've assumed that stuff is like censored at random?
Yes.
And you assume non-informativeness of censoring?
I have assumed both of those things, and I'll go back to the basics on how to derive it when it becomes a little more difficult. So the reason I put this on the board is mostly because this is an equation that some of you, if you've looked into the math behind survival analysis, would have come across and recognized. Which brings us, as Rajesh mentioned, to the problem. Many recent machine learning methods sort of extend linear models of survival analysis to nonlinear risk functions by changing the function f. So if you change it, for example, to something like a neural network, you might recover families such as the Deep Serve model that you may have used the software package for. And this is good because it allows you to enable nonlinear risk functions. But as Rajesh mentioned, they make the implicit assumption that the event and censoring time are conditionally independent given the covariates. So what does that mean? Simply put, it says that if I were to tell you what the covariates of the patients are, then it's as if someone were flipping a coin to decide when in the patient's journey they might be censored, which is to say that there's no correlation between the time that a patient is censored and the time that an event happens. And we'll talk through an example of when this might be violated later, but you might already, given some of your practical expertise, think of scenarios where that situation is violated. And indeed, in practice, it often is. So for example, if our goal were to build a model to predict treatment response to medication, then we would do our best to work with clinical domain experts to collect patient clinical features as well as demographic information. And we'd pack all of the things that we thought that were important into this covariate X. But the problem that we run into here is that there may be a patient who has an unobserved genetic trait, or there may be environmental factors that affect their response to medication. And this does not show up in the set of covariates X. And if you're working with the domain experts who suspects that this may be the case, then you run into the problem of dependent censorship. Because what could happen is that as the patient is working their way through the study, they may leave the study as they get sicker because they're not responding to medication. And the fact that they leave the study as they get sicker means that their censorship time starts to be dependent on their event time. And this is a practical problem that happens in a variety of different real-world scenarios with real-world data. But it is an assumption that many existing survival methods make and sort of don't handle elegantly, at least. And so this problem is what we'll refer to and is referred to in the literature as dependent censorship. So what do people do right now about dependent censorship? And I've definitely been guilty of this in past work, but this is a pretty accurate depiction of what a lot of methodological work might do when encountered with the problem of dependent censorship in survival analysis, which is assume the problem away. So when Russ and I and Ali and Michael sat together to think about this problem, we're like, what can we do about this? This is a problem, people recognize it's a problem, but at the same time assume that it isn't a problem. So how can we think of modeling survival data under dependent censorship? So that's going to be the bulk of what I talk to you about in the next 20 minutes. And the roadmap of what I'd like to get through is that I'm going to tell you why dependent censorship forms an impossible learning problem. I'm then going to motivate why copulas present one potential way as a mechanism to overcome this, and I'll end by talking about some of the hardness of evaluating survival models under dependent censorship. So let's go back to thinking just about these two random variables, the event time and the censoring time. And if we were to just plot the joint distribution between these two random variables and pretend that it looks like this cartoon figure over here, we can ask what happens to a patient who experiences an event at some point time t. So t here in this red dot means we can look at the intersection of where in this joint distribution this patient's data actually lies. And if they experience an event, we can carve up the space of this joint distribution based on the conditions of whether the event time or the censorship time is larger. And if you recall, when we want to train a model via maximum likelihood estimation, we care about capturing the event that actually occurred, which in this case corresponds now not to a single point, but rather to a slice of this joint distribution. We want to maximize the likelihood that the event time was actually t, and the censorship time was greater than that point where the event actually occurred. And so that corresponds to an integration from tc all the way to infinity. And you can write that mathematically as this integral that you see in the top, where the lower bound of the integral is the observed time, the upper bound of the integral is infinity, and this is nothing more than the conditional likelihood under the assumption that ti is where the event was observed. And you're integrating over tc, which is the censorship time. And you can do the exact same thing for the event time as well. So remember, you have patients who observe the event, and you have patients who are censored. And so these two integrals basically cover the two cases of event time as well as censorship time. And the problem that we run into, however, is that these integrals are intractable to evaluate and take derivatives with respect to, which is one of the conditions that we need in order for us to be able to train predictive models in this scenario. So we're trying to model a joint distribution of TC and TE from observations of either one, but never both. And so statistically, this is an impossible learning problem. And so I put this meme up, which my student generated as a motivating tool for how to think about why copulas might be a potential solution to this. And so copulas are a probabilistic tool that represent a joint distribution over the unit interval. But you should think of them as essentially a function that has a parameter that allows you to model the dependence between two marginal distributions. And so a uniparametric copula, which is a parametric copula with a single parameter, might allow you to model the dependence between two marginal distributions as follows, where on the x and the y axis are the marginal distributions of two random variables, and as the parameter increases, it sharpens or loosens the dependence between these two random variables. Now remember, in our case, the two random variables are event and censorship time. And so just as a thought experiment, I sort of asked GPT-4 to explain what a copula might look like to a 10-year-old. And I wanted to read out the answer, at least for one of the copulas, because I thought it was an interesting way to explain what a copula is. So it says, great, let's use the analogy of soccer and basketball, two popular sports, to help explain copulas. And you can think of the Frank and the Clayton copulas, which are specific choices of copulas, as special team scouts. So these scouts are trying to figure out how good players are at both soccer and basketball. And so for the Frank copula scout, the scout doesn't care about how someone is at just one sport, soccer or basketball. Instead, the Frank scout is really interested in how much being good at soccer has to do with being good at basketball, and vice versa. It's looking at how the two skills connect. And so if the Frank copula scout gives a high score, it means that kids who are good at soccer also tend to be good at basketball. But if it gives a low score, it doesn't necessarily mean that the kid is good at one or the other. So this is an interesting way to think about modeling dependence, and it's certainly not the only way, but it is the one that we adopted to choose for this work. And I won't read through the description of the Clayton copula, and you can check it out on the slides later, but the crux of what enables us to do this is a variant or a theorem called Sklar's theorem. And what Sklar's theorem says, and this is adopted to the survival analysis case, is that you can write down the survival function for these two random variables, the event and the censorship time, as a function of this copula. And so as a function of the copula, which in turn depends on the independent survival functions for each of them independently. So you can take these two random variables, TE and TC, the event and the censorship time, and you can couple them together. And you can use that coupling to model joint dependence between event and censorship time. And remember, that's the overarching goal here, to model the dependence between event and censorship time so we can have an elegant way to handle dependent censorship in the overall problem of survival analysis. And so here's a cartoon depiction of how a copula might work. So let's say you observed an event at time TE. You would map it onto the quantile of the copula. Given the choice of copula that you made, that would enable you to sample a quantile of the censorship time, which you could then map back onto TC. So copulas are probabilistic tools that don't couple the random variables directly, but rather couple their quantiles. And so I won't go into a lot of the mathematical details behind the machinery to make this work, but I will just say this, which is that you can take a copula and use it to replace that intractable integral that we had with an analytic function that is a that is a function of the parameters of that copula. So the integrals that we had a hard time evaluating and differentiating in the first set of equations that I highlighted can now be replaced by this derivative of u1 of c evaluated at some complicated set of points. So even though that equation looks complicated, you should take my word that you can translate that into a simple analytic and differentiable function. And that's really the trick that makes this entire enterprise work. And so instead of those two instead of those two intractable integrals, we end up with two functions of the parameters of the copula that we have. And these functions are good because they're tractable and they're differentiable, and they represent the likelihood of the data that we observe, which means that we've taken copulas and turned them into a tool that makes learning feasible when you have dependent censorship. And so the specific choice of model that we actually end up using here is what's called the Weibull-Cox proportional hazards model, where we have a baseline hazard that depends only on time, and in purple, a covariate hazard, which is going to be parameterized with a neural network as a function of the covariates. And so I've provided the equation here for this choice of the proportional hazards model of what the survival function and the event function looks like for this model. And learning the model really follows these three steps. So what we're going to do is we're going to instantiate two of these models, one for the event time and one for the censorship time. And then we're going to instantiate a copula to couple the event and censorship time models that we just created. And we're going to jointly optimize the parameters of all three, the event time model, the censorship time model, and the copula model. So it kind of looks like the diagram at the bottom. And so just as a pulse check on the story so far, we wanted a model of nonlinear survival risk that worked under dependent censorship. We used copulas as a mechanism to induce dependence on hypothesized relationships between event and censorship time. And doing so leads to a loss function that is differentiable, and we can use standard autodiff packages to take gradients with respect to the parameters of the model that we have. Okay, so let's say that we're successful in learning a model under dependent censorship. So how do we actually evaluate it? One of the gold standards ways to evaluate a survival model is the concordance index, or the Breyer score. And this represents one of the important challenges that we ran into when trying to actually write this work up, which is we did the work of coming up with a potential solution to dependent censorship. But what we found is that existing metrics for survival models did not accurately reflect the ability to rank models under dependent censorship. And so in this example, you can focus just on the C index. We took a data generating process and we created synthetic data where we changed, and this is along the rows, where tau represents the intensity of the dependence between event and censorship time. So we created synthetic data where we knew what the underlying copula actually was, where the event and censorship time had varying degrees of dependence. And after that, we looked at what the C index looked like for the uncensored data as well as the censored data. And essentially, we found that they were different, even though they represented the same base set of populations that should have had the same degree of probability of ranking between pairs of patients. And so, given some of the experiences that we had with the existing set of metrics, we came up with our own metric that we call the survival delta metric, which represented the bias in the estimated survival curves, which were the norms of the difference in the survival curves for the observed events and the predicted events under the model that we described a few slides ago. So we would predict the risks, and using the predicted risks, create a survival curve. And then we had the ground truth survival curve because we had access to the data generating process. And I should highlight that this is a limitation of this metric because it does require access to the ground truth risk function. And we would simply look at the difference between the two. And what we found, and you can focus on the left side of the plot first, where the dotted lines represent a model that was trained without a copula, and the solid lines represent a model that was trained with a copula, which is that having a copula enables you to control for dependence across a wide variety of parameters that capture how tightly event time and censorship time are correlated. But this is sort of a very synthetic example, and we wanted a real-world example that might be a better fit to understanding how these methods might do in practice. And the problem that we ran into is that every real-world data set for survival analysis uses the C-index, which we knew to be unreliable as a means to test dependent censorship. So what we did instead was took a regression data set, and for the training set alone, we created censored data under varying degrees of censorship. So we could change by using a copula how tightly correlated the event and censorship time were in a regression data set. And once we had a risk model that was trained under dependent censorship, we could evaluate it using R² on an uncensored test set. And that gave us another measure on how well these two models do, where we find that the no censoring model is sort of the upper bound on how well any model could do on this data set. And the dependent model, which actively captured the censorship time during training on the censored training data set, that was able to have a better R² on the uncensored test set when we evaluated it. And finally, in the earlier parts of the talk, I talked about having three models: a censoring model, an event model, and a way to couple the two. In some of the more recent work that we've been doing, we've been capturing the intuition in deep learning that perhaps it suffices to have a single shared representation for both the event and the censoring model. And so we tried that, where the model, instead of having three models, has only two models with a shared head to capture the shared representation that between censoring and event time. And it turns out this model, and this is negative log likelihood, does quite well on the nonlinear risk functions that we evaluated it on. So I'll start wrapping up here. In summary, what we showed is that copulas present one way to relax the assumption of conditionally independent censorship in nonlinear survival regression. We give a mechanism to create a neural network-based model of survival that does not assume conditionally independent censorship. And we highlighted the problem of metric bias, as well as some of the connections to causal inference. And in the paper, if you're interested, you can read more about extensions to convex combinations of copulas, as well as practical guidance on how to choose the right copula. So with that, thank you very much. Here's some references, both our own work as well as work out of KU Leuven, which is very recent, on thinking, and that's more from the stats community, on thinking of how some of these ideas could be adapted for linear Cox proportional hazard model. So thank you for your time.